All right, I'm going to tell you a little bit about scalars and vectors in this video. I'm going to start with just defining scalars and vectors. Then we're going to talk a little bit about vectors and their properties. We'll talk about how we represent them mathematically and graphically, and how we coordinate between those two representations. So first, let's just start with a very basic definition. A scalar in physics is any physical quantity that can be represented by just a number. So that would be something like mass or volume, where the amount of stuff or the amount of space it takes up is all you need to know about the mass or the volume of that quantity. A vector, on the other hand, is a physical quantity in physics that has a number and a direction. So I might say I'm driving 40 miles per hour. That would give you the number, but it doesn't give you the direction. I would have to say I'm driving 40 miles per hour east on Grand River. That gives you my velocity, which is a vector quantity. Other vectors that we'll run into, things like acceleration, force, and so forth, are all vector quantities that we need to know how to do mathematics on and to represent visually. So what we'll do is we'll talk about vectors, and we'll talk about how we represent them visually first. So here's how I would represent a vector. The bit on the end here is called the tip, or the head. The flat part down here is called the tail. Notice it just looks like an arrow. This vector is actually exactly the same as that vector. Both of them have the same number, they have the same size or length, and they have the same direction or orientation. So it turns out it doesn't matter where the tail is. All that matters is how long the vector is and which way it points. So this is a way of graphically representing that vector. We're going to put it on a coordinate system here in a moment. Mathematically, we represent vectors with a symbol and an arrow on top. That tells us that this quantity is a vector quantity, and typically it'll have 3 digits which characterize how much of that vector lies in each coordinate direction. So in three-dimensional space, x, y, z space, the amount of this particular vector that lies in x, y, and z represent the components of that vector r. Okay? So we have both sort of a graphical understanding and a mathematical understanding. We're going to coordinate between these two. So typically, these vectors are in 3 dimensions. I'm going to limit it to 2 dimensions because it's easier to draw. So I'll draw an xy plane, and I'll draw some vector in that plane. I'm going to label this vector. I'm going to call it vector r. This is typical for us. We call these kinds of vectors position vectors, because they identify a location with respect to the origin, typically. Now, if I want to know about the components of the vector r, all I would do is measure along the x-axis how much of this vector is along the x-axis. That's the x component. And how much of this vector is along the y-axis. That's the y component. So in the 2-dimensional space, it's pretty easy to visualize these components. But what you might have is different information about your vectors, and you need to coordinate around that information. So, for example, another way of defining a vector is to tell me how long it is. That is, what's the size of the vector, and what angle does it make with the positive x-axis. Now we have lots of information, and we have to figure out how we coordinate between all of that information. So the first thing we're going to do is we're going to figure out how long that vector is. So if we look at this picture, this corner right here forms a right triangle. And so we can compute how big that vector is, what's its magnitude, by just using the Pythagorean theorem. It is the sum of the squares of the components, square root. The other thing we can do is we can figure out what the angle that vector makes with the x-axis is going to be as well. And we can do that using trigonometry. We know that if we have these components, the tangent of this angle is equal to the ratio of the opposite to the adjacent side. So we can determine the direction by taking the ratio of the opposite to the adjacent side, or the y component divided by the x component. So this information gives us both the size and the orientation if we know the components. We can actually go the other way, and given size and orientation information, we can determine the components. And that's, again, using trigonometry. If we consider the length of this vector to be its magnitude, r, then this is the hypotenuse of a right triangle. And so the component in the x direction is the magnitude of that vector times the cosine of the angle. And the y component is the magnitude of that vector times the sine of that angle. And so this gives us the components from the size and orientation information that you might have. So both of these are very useful representations. They coordinate the math with the graph, but they also help us to understand how we would use these given particular information. Now, one thing I'll make a mention of, this angle was measured specifically from the positive x-axis in a counterclockwise fashion. And so these trigonometric functions are all defined in terms of that orientation. So if you have a different type of problem where you have to orient the problem differently, these trigonometric functions might not work for you. You're going to have to go back to this triangle and figure that out again. All right, one last thing we're going to do is we're going to add some vectors together. And the first thing we're going to do is we're going to actually do it graphically. So we'll draw again another xy axis. We're going to take some vector A and some vector B. And we're going to talk about how we add those together. Okay? So what we'll do is we'll use the so-called tip-to-tail method, which is why we introduced the idea of the tip and the tail. And we'll put at the tip of A, the tail of B. So if we draw A like this, and we draw B like this, this is the tip-to-tail method, then the resultant, or the vector which points from the tail of A to the tip of B, is the sum of A and B. If we do that on a coordinate axis, so if I go ahead and erase this, and I do it on this coordinate axis instead, what we can see is we will get the component of A plus the component of B in the x direction. So we'll add up AX and BX. And we'll get the component of A in the y direction and add that to the component of B in the y direction. So in fact, we know how to add vectors together when we have components. If we add A and B together, it's just the scalar addition of their components. Okay? So this is just a brief introduction to the idea of vectors, how we coordinate between graphs and math, how we do a little bit of the addition, and how we coordinate the addition both mathematically and graphically. There's a lot more notes on the website that you should probably check out. Talks about unit vectors, and it talks about vector subtraction. These are things that I didn't cover in this video, so you should pay attention to those.